Welcome for the third talk. So we have speaker Jongchon Kim, City University of Hong Kong. He will speak on Nikodym sets of per sphere and related maximal functions. Please.
Okay, thank you very much for the invitation to visit India. It has been my pleasure to be here. And thank you for giving me the opportunity to speak. So I'm going to talk about Nikodym sets for sphere and related maximal functions. And this is going to work with Ellen Zhang and George Dosidis. So, okay, is this big enough? Okay, so let me know if I start to write a bit too small or if you have any questions or comments. Okay, so let me first introduce a couple of sets which behave in a somewhat weird way. So there exists a set, let me call it A, on the plane of ribbon measure 0. Okay, such that, so firstly, I will consider a Baskovich set. Okay, so Baskovich set was considered in Josh's talk. So for any unit vector, which I will think of as a direction, there is unit line segment LE contained in A, okay, in direction given by this unit vector. Okay. So if this is a unit vector, then the set A contains this line segment in the same direction. And for every direction, still having the ribbon measure 0. Okay, and there is an analog of this Baskovich set for circles, also discussed appeared in Josh's talk. So this is often called BRK sets. So for every R positive radius, there exists a circle CR of radius R contained in A. So, okay, so for any given R, we have this circle contained in this set, and maybe for a bigger radius, it is also contained in there. But still have ribbon measure 0. Okay. And thirdly, let me discuss Nikodym set. For any point on the plane, there is the unit line segment Ly containing that point Y, okay, such that one-dimensional Hausdorff measure of Ly minus A is 0. Okay. So okay, for a fixed point Y, Ly can be this linear line segment. And for some other point, it can have a different direction. Okay, and this roughly saying that Ly is contained in A up to some negligible portion of this line segment, of measure 0 part of this line segment. Up to that part, it's contained in this set A. And still have Lebesgue measure 0. An analog of Nikodym set for line segment for circles, unit circles, was recently discovered by Ellen Chang and Sune. So let me write it down. Nikodym set. For unit circles. So for every point on the plane, there is just unit circle. So Cy containing Y, such that one-dimensional Hausdorff measure of that circle minus A is 0. So now for fixed Y, it contains a unit circle passing through the point Y. And this set contains this circle up to measure 0 portion of this circle. Right. Are there any questions or comments so far? Yeah, so at least I need to remove at least one point here so that it can have Lebesgue measure 0. Yeah. Okay, I think for line segment, I think removing just this point Y is enough. For circles, I think they need to remove 2 antipolar points. That is enough. Okay. Example of BR cases. Yeah. Example. The construction, okay, maybe I cannot tell you in detail about the construction, but as far as I understand,
I'm saying, suppose some positive measure condition, if we just think of on the set A, then what will be the, like, can there be any example? Like, suppose we think in the analog of this Besicovich set, suppose I consider, if we remove the assumption like Lebesgue measure 0, say Lebesgue measure some number, then circle, disk I can think of rotating. Then analogous example in the BRK set.
When we just
some positive,
assign some positive number for the measure, I think it can be constructive.
Okay.
Yes. So maybe by looking at the circles of every radius in between this and these circles, we can maybe cook up some measures so that it matches with the given number.
Oh yeah.
And all the other maybe circles to maybe coming from this BR cases. Yes, I think the answer is yes.
Okay, this kind of sets. Yeah. Okay.
Okay, thank you.
So in the second and third definition, so does that give you any lower bound on the Hausdorff dimension of A?
Oh, okay, that's a good question. So, right, so yes, so the question is how small can those sets be really? So the answer is that it cannot be, it can be small in the sense of Lebesgue measure, but it cannot be too small in the sense of Hausdorff dimension. Okay. So I will talk about this. So these sets, they all have Hausdorff dimension 2. Okay, so which is the maximal dimension that those sets can have. Okay. And there are n versions of this sets exist. So one can ask similar question about their Hausdorff dimension. Okay. Right. In the case of Kakeya and Nikodym set, okay, for line segment, okay, this is so I didn't ask the question. So for the question is, it must they have Hausdorff dimension n. Okay. And for the case of Kakeya and Nikodym set for line segment, this is the Kakeya set conjecture. It predicts that the answer should be yes, but this is currently open in dimension bigger than 2. Okay, for the case of BR cases, the answer is, complete answer is known in every dimension. So the answer is yes, and this is due to Kolasa and Wolf in dimension bigger than 2. And in dimension 2, this was proved by Wolf, which turns out to be more difficult in the case of circles. All right, and for Nikodym sets, as for circles, the answer is also yes in every dimension. And this is, this follows from bounds for certain maximal function associated with spheres. Maybe I should say spheres, not circles. So I will talk about related maximal functions, which have, whose consequence is about dimension of Nikodym sets for spheres. Nikodym sets, okay. So here, regular Nikodym sets, those Kakeya set conjecture and the conjecture for Nikodym sets are known to be equivalent. So I'm just saying, okay, I'm writing this all together here, and these are still open, big open problem in harmonic analysis. Okay, and each of those sets, there is related maximal function. Okay, so here, delta will always be some small fixed real number. Okay.
Hello and welcome back, fellow path integrators. Today we're going to solve the Basel problem.
Yes, this also in all dimension. And okay, maybe I should say a bit more about this. So here they constructed this Nikodym set for unit circles, and a larger class of Nikodym sets is the case when we don't require circles to be unit circles. So if there is this type of sets, which not necessarily be constructed from unit circles or unit spheres, they still must satisfy this Hausdorff dimension condition. Yeah. Okay. So let me write m delta f w to the maximal function associated with certain curve in CW, a set to be defined. Okay, so this indicates average of f over f delta, which is delta neighborhood of the set S. Okay. And okay, for the Baskovich set, so in this case, W is a unit vector, okay, and CW is set of all the unit line segments in direction E. And for BR cases, W will be any positive real number, and CW is set of or circles of yeah, thank you. Okay, great. Okay, so of radius W. Okay. And for Nikodym sets, in this case, W will be any point on R2, and CW will be a unit line segment. Okay, containing W. And for Nikodym set for unit circle, we can replace just unit line segment by unit circle. Then, okay, then those are related to maximal functions associated with those four sets. Okay. And each of these cases, there is trivial L infinite estimate. So this denotes L infinite operator norm, and this is one. However, if we look at LP operator norm for finite P, this LP operator norm goes and blows up as delta goes to 0. So if we take primum of over delta, then this operator norm goes to infinity. And this is due to the existence of measure 0 Kakeya set and Nikodym set and Nikodym sets for circles. Okay, so for any finite p. Yeah, for any maximal functions associated with those four type of sets. Yeah, yeah. I think weak type, because weak type we can interpolate, if there is weak type estimate, we can interpolate to get strong type estimate. So I don't think weak type estimate will be available as well. Yeah. Okay. Okay, so from now on, I will focus on the maximal function associated with unit spheres. So let me use this notation m delta f of x to be the supremum of the average of function f over s delta, where s is unit spheres containing the point x. Okay. For any point x, we take average over unit sphere containing this point x, and then take the supremum over all choice of unit sphere. Okay. And then because the LP operator blow up as delta goes to 0, we may ask how fast it blows up, or what is the rate of, what is the operator for this m delta. Okay, so we will ask, so given the dimension and, excuse me, and p what's okay, optimal alpha such that we have the following estimate. Okay. So by this, I'm allowing some logarithmic term, such as, so I'm allowing this type of loss, which was for arbitrarily small epsilon, okay, to indicate this notation. Pardon? Yes, yes, right. And this will also, okay, so given this, for example, when we have estimate of this type, yeah, then this will be covered by this type of notation. Is that clear? Okay. Okay, second question is, what happens if we vary the radius? Okay, so we not just take average over delta neighborhood of unit spheres, we can consider taking delta neighborhood of, taking average over delta neighborhood of some spheres of radius comparable to 1, okay, containing this point x. So let's take delta f to be supremum over all spheres of radius comparable to 1, and then we take the average. And then we can ask the same question: what's the LP operator norm of this operator in terms of delta? Okay. And considering this is essential when we want to say something about Hausdorff dimension of Nikodym sets for spheres, which we allow spheres to have radius not necessarily E1, okay, which can be arbitrary radius. Okay, so we consider this problem as well. So yeah, I will start with the bound for n delta. Okay. Okay. All right, so let me start by giving you some examples. So let's study this ratio for some indicator function of a set E. Okay. So first, maybe simplest example is when E is a delta neighborhood of a unit sphere. Okay. Okay, so let's say this is delta neighborhood. Okay, let's say this is E. And let's consider the one point X on this sphere, on this delta annulus. Okay. And in this case, I can find a unit sphere contained in this delta neighborhood. So for such X, is n delta on X. So this is comparable to, this will be comparable to the size of E because, okay, so this is Sx, where if I denote this yellow sphere by Sx, and this will be the delta neighborhood of the sphere. Okay? And then we divide this by the delta neighborhood of this sphere. Okay? And this delta neighborhood is essentially the same as E. So this is comparable to 1. Okay? So this maximal function is comparable to 1 on this set E. So we can say that this ratio is at least 1. Okay? So it cannot be much smaller than 1. Right, and let me consider another example on the plane. So let me consider delta ball. Okay. And delta ball is contained in. Okay. So let me draw this delta annulus. So let's say this is delta unit annulus. And if X is a point, say in here, and I can take the sphere, this sphere, to be this one, so that the delta neighborhood of this Sx contains this delta ball. Okay. So if we do this calculation, then in this case, n delta this will be about this volume of this delta ball. Okay, let me write this as B delta over the volume of, okay, as X delta, which is about delta. Okay. So the size of this Maximal function is about delta when X is in this annulus, delta annulus, but we can take another delta annulus, okay, like this, and so on. So in fact, this X, for any X in the set of measure about 1, we have this size estimate. Okay. So yeah, we just do such computation, and we will get the following lower bounds. Okay. Okay, so when dimension is equal to 2, the delta ball example gives us one lower bound. And we get delta. Okay, the size of this is about delta. And then because of this factor, we will have deltas 1 minus 2 over p. And then in dimension 3, there is another relevant example. So we call this as tube. So this is tube of radius delta with length root delta. And if we consider this, then we get another lower bound. Yeah, there's yet further lower bound example, which we will go through in there. So this is Sn minus 2 times the interval 1 to root delta. And then we take the delta neighborhood of this set. Okay. So then in this case, we get this lower bound. Yeah. Yeah, so in dimensions bigger than 2, yeah, this example is not effective, not so strong example. So instead, these two examples are better. Yeah. And for n bigger than 3, there's yet another example which plays a role here. This. Which we call range type example, or 1 over root, okay, of sphere of radius 1 over root 2. So this one is, okay, it's this one. Okay, this is defined to be delta neighborhood of this product of 0 and this sphere of radius 1 over root 2. Okay, and this gives us lower bound delta 2 minus 3 over p. Okay, so okay, maybe let me just make one remark about this example. So for y contained in, so why that last example is relevant, so how we use that. So when y is in this set, it turns out that the set that we just mentioned over there is contained in the translate of unit sphere, translated by y. And this holds for every y inside of this set. So this is how we use that example to get this lower bound. Okay, and then after we have obtained several lower bounds, and then we compare which one is strong at which p. And then after we compare this, we get some critical exponents. Okay. So, and this gives a possible critical exponent. Okay, so for p equal to 2, when n is at least 2, so this is one critical exponent. But when dimension is 3, we have another critical exponent, p over 2, 3 over 2. And then yet another critical exponent exists, which is 4 over 3, when the dimension is bigger than or equal to 4. So, sorry, but I'm not quite remember this. It can be only dimension. Yeah, right. This is right, yeah. Okay. So now question, then the question is if this is a really critical exponent, and if so, how we can obtain this estimate at these exponents. So if we are able to obtain correct estimates for those critical exponents, we could interpolate them to get sharp estimates for every p. And this is So for example, for n equal to 3, we compare these two. And then we consider, for which p this matches together. Okay. And then, for some p, this is stronger, and for certain p range, this is stronger. So that determines these exponents. Okay. And this is our theorem. So let me just write CDK for our Chang and Dosidis and my stuff. So for n bigger than or equal to 2, the L2 operator norm is about 1. So to be precise, we in fact have this in terms of logarithm. For n equal to 3, we obtain bounds at the critical exponents, and then we get this estimate, delta to power minus 1 over 6. And in higher dimensions, we study this estimate at the critical exponent, and then obtain this estimate. Okay, and comparing this with the necessary conditions, those are all sharp. So if we interpolate this with trivial estimates, then we get sharp estimate for every P and N. So interpolate with trivial bounds. So the trivial bounds are L1 estimates and L infinity estimate. So we get then sharp LP estimates for all N and P between 1 and infinity. Okay. You mean this one? Yeah, we believe, yes, we believe this is sharp. We haven't written down whether this is sharp or not. We didn't care too much about these logarithmic factors. And this is, this coincides with also the norm, L2 operator norm for the Kakeya maximal function discussed yesterday. Okay, so this is the time left. 13 minutes. Okay, then let me introduce how we obtain such estimates. So by using some proof ideas. So using duality and some discretization argument, we are led to study this type of estimate for LP prime norm. Okay, so here, let me write xi is to denote a maximal delta separated set of points on a unit ball. And then the collection of spheres, okay, this is a collection of unit spheres such that Si contains the point Xi. So we have to study this type of estimate for those collection of circles or spheres. Okay, and then we notice that when P is 2, this will become 2. And when P is 3 over 2, the dual is 3. And when P is 4 over 3, the dual is 4. So we can expand this norm into some summation, multiple summations. Okay. Okay, so right, let me start with the case P equal to 2. So we have to understand, in this case, we have to understand, we have to study intersection of two delta annulus. And typically, when their centers are about 1 separated, their intersection will have, okay, this is intersection. So their intersection will have a volume about delta squared when they are about 1 separated. So on average, that's what happens on average in the worst possible case. So in this case, okay, for any fixed I, if we sum S delta I intersected with S delta J, and then take average of over J. So, okay, note that number of J, there are delta to minus N J's. So this is, we can bound this by delta square. And this is enough to prove that L2 estimate. And for L3 and L4 estimate, we have to consider intersection of 3 annulus and 4 annulus. Okay. And then regarding that, those bounds, we have the following estimate. So for any fixed I, when dimension is bigger than or equal to 3, if we take the average over of this sum of the intersection between 3 years, 3 annulus, and this is at most delta to the power 5 over 2. And in the case of full the intersection of 4 annuli, we have about delta to power 3. Okay, and this, okay, so we study this intersection of 3 annulus, and it turns out that it depends on the circumradius of the centers of those annulus. So we do some case-by-case analysis, and then we obtain this estimate. And in the case of higher dimensional case, fortunately, we didn't have to study intersection of 4 annulus. So the reason is one of them don't contribute too much to this volume estimate. So we could remove 1 annulus without too much loss. So we can just apply the the bound for intersection of 3 annuli, and that was enough. 3 annulus? Yeah, I can maybe briefly mention about this. So let's say these are centers of the annulus. Okay. Now we consider this triangle, and this is smaller side, and let's say M is longest side, and then we let R to be the circumradius. Right. Then case 1, when M is less than root delta, in this case, we can safely remove 1 sphere. And and this intersection considering intersection between only 2 annulus is enough. Okay, so this case can be done by using 2 annulus. And then we look at the case, and this is bigger than root delta. And when circumradius is much bigger than 2, there is no intersection. Okay. And when this is about 1, and in 3-dimensional case, the volume the intersection volume is about delta to 5/2 divided by m3/2 to m1/2. So we do this type of analysis. So, and when n is bigger than 3, or circumradius is less than 1/2, we get a better estimate, which is delta to power 3. So yeah, those are some elementary computations. And then applying this estimate, you were able to prove the lemma. And then that gives the result stated here. Okay. Okay, now moving to the second topic. Now let me recall that S delta is about a sphere of radius comparable to 1. And it satisfies the same trivial estimates. And our result is that in dimension 2, the L2 operator norm, L3 operator norm is bounded approximately by 1. And in higher dimension, the critical exponent turns out to be L2. And this is bounded approximately by 1. Okay. And this is sharp. And if we interpolate this with trivial bounds, L1, L infinite bound, we get sharp estimate for every P and N. Okay. Sharp examples, let me talk about sharp examples. In this case, it is enough to consider a delta by root delta box. And in higher dimensions, we consider range type example again. And this shows sharpness of those estimates. And interestingly, these are sharp examples for the maximal function associated with ER cases. So the maximal function considered by Wolf, Kolassa, and Wolf exactly satisfy the same type of LP estimates written here. And the reason why it has to satisfy the same LP estimates might be similar because we share the same sharp examples. So now let me talk a little bit about the proof. So for L2 estimates, we again use duality, and the argument for N delta just carries over to this setting. Now for L3 estimates, we need some bounds for now P prime is L3. Okay, we need to study 3/2 LP. Okay, L3/2 norm, and no longer unisphere but spheres of radius 1. And in this setting, the estimate that we need was precisely proved, was known by the work of, okay. yeah, the work of Ulf. And which was later generalized by Harmonic, Yang, and Zhao. Okay. Let me just state this result and finish. Okay. So here the setting is that C is collection of circles centered at xi with the radius ri. Okay, and here ri is comparable to 1. Okay, then let me write this as non-concentration condition. So that condition is that as a point in R3, okay, we count the number of indices where this is contained in a ball of radius rho, which is 3-dimensional. So we take supremum over all B rho in R3, okay, of radius. And then for every row bigger than or equal to delta. And if this is bounded by a rho over delta, so somehow indicates that those set of centers and radius is somehow 1-dimensional in nature. If this is true, okay, then one can say about that desired estimates. Okay, so okay, this is trivially true when those annulus are disjoint. But when, okay, in general situation, as long as this is satisfied, they were able to conclude that this estimate holds. And this estimate was first proved by Ulf in the case of circles coming from the case of BRK sets. Okay? And then later it was generalized in this form by Pramanik, Yang, and Zhao. And this applies to our case. So we were able to just use this estimate in our proof. Okay, thanks for your attention. I will stop here.
Is there any question from online?
Oh, yeah, good, very good question. Yes. So, okay. So we know that they cannot be bounded uniformly in delta, right? The LP operator not blows up. So we want to consider some variant of those maximal functions where we take smaller, okay, supremum over smaller families of spheres. Okay. So that those estimates are bounded uniformly in delta. So eventually we want to get rid of delta and then just take average over a sphere. And then, but that is only possible when you consider smaller families of spheres. So I'm going to talk about that on Friday.
You mean lacunary delta on a thinner set?
So here we consider, if given point x, we consider, say, every unit sphere passing through this x. But then now we don't want to do that, but just consider smaller families of unit sphere passing through x. And then the question is how small that should be if we want some uniform LP bounds.
restricted set of directions.
Right, right. So this can be, yeah, considered as associated with direction U. And yes, and we will take a smaller number of directions, or smaller size of directions in our estimate.
Is there any questions? Any other questions? If not, let's thank the speaker.
Thank you.